So to construct this function, I just need to fill in the pieces here. So x2, I'm just going to leave as x. From the function here, there's x minus x1. x1 is the first coordinate 1 here from the point 1, 1. So that squared plus y2, but y2, right, is our second coordinate in the abstract. It's 5 minus, oops, sorry, there should be a 2 there. 5 minus 2x. 5 minus 2x for y2 minus y1 minus 1, quantity squared. All right, so there's our distance function, all in terms of just x. If we minimize this function, we should be able to find out what x value makes this the smallest. So the only thing now is, I could go ahead and take the derivative immediately of this with respect to x, but it's easier if I should get rid of this radical. Okay? It seems a bit strange I can just discard the radical, but the idea is this. If I'm trying to minimize a radical function, right? Now I'm not looking for the minimum value. The question didn't ask me what is the shortest distance between the line and the point. It asked me where is this line closest to 1, 1. So that means I'm looking for a point. It means I'm looking for an x value. So I'm really just trying to find the x value that creates the absolute minimum here. So I'm not looking for the absolute minimum itself. So therefore, if I want to find the x value that minimizes the radical function here in totality, it's the same as finding the x value that minimizes the argument inside here, right? Because if I can minimize this quadratic in here, then applying the radical to it will also leave that minimized, right? So let's discard the radical and clean up this quadratic. I'm going to go ahead and write d again. Maybe I'll use a lowercase d or something. I'll use a lowercase d. It's changed. I'm changing this a little bit. You could use anything here, but this will be sufficient. Okay, so lowercase d, I'm going to discard the radical, and I'm going to clean up this quadratic. So we have x minus 1 squared plus 5 minus 2x minus 1 is negative 2x plus 4 quantity squared. Let's just keep simplifying this as much as possible before we take the derivative. So minus 2x plus 1 plus 4x squared minus 16x minus, or plus 16 I should say. So we'll have that, and just keep combining like terms. X squared and 4x squared is 5x squared, and negative 2x and negative 16x is negative 18x, and 1 and 16 is 17. All right, so there is our distance function, a little bit altered, without the, basically just without the radical, and cleaned up a little bit. So d equals 5x squared minus 18x plus 17. I just want to take the derivative now and find out what x is. So d prime would be 10x minus 18, set equal to 0, and solve. So we will get, well, I can factor off a 2, I guess, or you could just solve it very quickly. Either way, it doesn't matter. Let's just solve it. So 18 divided by 10, all right, we will get x equals 9/5 or something. So 9/5. Okay. X equals 9/5. Now, I should go ahead and use the sign chart to ensure that this is a minimum. So sign chart. I have something like 9/5 somewhere in here. It doesn't really matter where. So if I take it 9/5 and break up the real number line into two distinct subsets here. So I'll take a test case from before 9/5, amount to 0 or something. So 0 back in the derivative, right, will give us a negative here. So that means the distance function derivative is negative there. Therefore, the original distance function is decreasing there. And then on the right-hand side, you can pick anything larger than 9/5, and you'll see it's going to be positive. Okay, pick 1,000, right? Clearly 1,000 in here is going to make this positive. All right, so that means the original distance function is increasing there. So if it went through a location where it was decreasing at first and then it changed to increasing, we must have a local minimum here. But this is not just a local minimum, because this is all that's happening across the whole real line. That makes this an absolute minimum, right? If the function was always going smaller until here and then it got bigger afterwards, this must be the lowest location. So we can see that x equals 9/5 is the location of an absolute minimum. All right, and so now we know the point, or at least the first coordinate of the point that will minimize the distance between the line and the point 1, 1. So we now believe that this point here that I highlighted in green earlier is 9/5, comma something. Okay, so the way to find 9/5 partner here in the dependent variable is just to plug it back into the line and see what you have. So we would have y equals 5 minus 2 times 9/5. So we'll have 5 minus 18/5. Giving a 5/5 to this, we'll have 25/5 minus 18/5 is 7/5. All right, so we got 9/5, comma 7/5. So if we look on the line that I drew and see how accurate this is, it's not too bad, right? 9/5 is like 1 4/5, so 1 here and 4/5 over. Yeah, that's about right. It's reasonable, right? There's 9/5 down there, and then 7/5 is 1 2/5, I guess. All right, so it's reasonable and not perfect, but reasonable enough, right? There's 7/5. So we have our answer, 9/5, comma 7/5, and the picture reflects that reasonably well in this case.